So the main topic is derivatives. So I'm going to start with taking some derivative practices. So I'm going to start with the sticky note. So let's say we have, I'm going to start with the rule of exponents. So let's say we had 3x squared. So we're going to want to take the derivative of that because some equations you're going to have to take the derivative in AP Mechanics. So basically what you have to do when you have an exponent, you multiply the exponent by the number in front of the variable. So in this case, it would be the 2 times the 3. And then what you do with the exponent is you subtract 1. So it would be 2 minus 1. So that's basically what you always do. You just multiply the top by the side number and then subtract 1 from the number. So in this case, the final answer would be 6x as the derivative. And the integral is basically just the opposite. So if you were to take the integral of 6x, you would come back to 3x squared. And so there are some other rules too. So these are just some rules you need to memorize. So the derivative of cosine of x is negative sine of x. And the derivative of sine x is positive cosine of x. And then for the integral, it's just the opposite. So the integral of cosine of x would be sine of x, and the integral of sine of x would be negative cosine of x. But that's just the rule. So you just have to memorize that. So I'm going to write that down for you guys. If you ever get confused between like integral and derivative, just try to remember the derivative and then just think the opposite. So just go backwards. This is going to be useful for like impulse equations and force equations because a lot of times all you have to do is integrate or take the derivative. It's also really useful for velocity, position, and acceleration because acceleration is just the derivative of velocity, which is the derivative of position. So here I'm writing up some basic equations to memorize. It'll be very useful to know these because then you can just go quickly and you don't have to like look it up because you won't be able to look it up on the test or anything. So if you want to find the integral, you just go to the end and go backwards. Here's another one for you guys to memorize. So the derivative of tan x is secant x squared. So that's just something to memorize again. And at the end, I'll show you guys how to apply it. Another example of using the derivatives is if the exponent is just 1, the x would just disappear. So let's say we have the derivative of 4x. It would just become 4. Now let's move on to integrals. So like I said before, you can just go backwards if you want to use integrals, or you might have to use a u sub, which I'll show you in a second. So let's say we have the integral of cosine of 3x dx. So in this case, it's not just a cosine of x inside, which means you have to do some manipulation. So I'm going to start drawing. So let's say basically what u is something that you can't like immediately like simplify. So in this case, instead of cosine of x, you have cosine of 3x. So the u would be 3x. And this is called u sub. So you write u equals 3x. And so basically there's another thing that you have to keep in mind. So it would be du, which is basically derivative of u. So as we said before, if the exponent of the x is 1, it becomes 0. So in this case, the derivative of 3x is just 3. But you always have to add in the dx at the end. It's basically like derivative of x, kind of. So here you see in our integral, the integral was cosine of 3x dx. So you want it to match equally. So let's say we have, right now we have 3 dx, but in this case, we only have 1 dx. There's no 3 outside the cosine of 3x. So in order to get that to be 1, we have to make it 1/3 du. So 1/3 of 3 is just 1, so that cancels, and it becomes dx. So now we have all our parts. We have the dx here and the 3x inside. So that covers every component of this except the cosine of x. So now we can take the integral. So we do integral of cosine of 3x dx. So now we substitute. So we know we have, instead of 3x, we now have a u. And here we have a 3 dx. No, 1/3. So we have 1/3 of cosine of u dx. So now we can pull out the 1/3 because any number in front can just be pulled out of. So now we have 1/3 the integral of cosine of u. And here we can just pretend the u is like an x kind of. So if we remember before, the derivative of sine of x was cosine of x. So if we want to find out the integral, it's just the opposite. So we have the cosine of x at the end means we have to go backwards to sine of x. So here it's going to be, the final answer is going to be 1/3. I'm going to use a sticky note. 1/3 sine of u dx. But now we have to substitute that 1/3 sine of u dx. So we just put what u equals, and we have u equals 3x here. So our final answer would be 1/3 sine of 3x. And so now it kind of like depends. So we don't have like a given number. So we're going to have to add in a plus c. And this is just a rule you're always going to have to remember. If it's not a definite integral, you're just going to have to add a plus c at the end. So this is our final answer of that integral. And as you can see, I kind of made it complicated, but if you just look at it, it's really just realizing that you need to make the 3 and the 1/3 cancel to make a 1. So you just add a 1/3 and it kind of ends up being the same anyway. So let's do another one like that. So sometimes there might be multiple parts. So we could have, let me write 4x squared plus 3x dx. So in this case, we just have to look at each individual part and take the integral of each part. We don't have to do any combinations or anything. So here we know that if we're taking the derivative, we subtract 1. So if we're taking the integral, we have to add 1. So instead of 2, it's going to be 2 plus 1, which is 3. And now we're going to have to make it so that the number in here equals 4 when it's multiplied. So in this case, it's going to have to be 4/3. So basically 4 divided by the exponent. If we took the derivative of this, which is the opposite, we would have 4 times 3 is 12. 12 divided by 3 equals 4, which gets us back to our original number. So now we know technically there's a 1 here. So x plus 1, 1 plus 1 is 2. And now we do the 3 divided by the 2, which is 3/2. And we always have to remember the plus c at the end. So we would add a plus c at the end. And this would be our final answer. So it's not too complicated, just to split it up evenly. So now let's go to a few more derivatives. So here's another rule. Let's say you have the derivative of e of x. In this case, it's just e of x. The derivative of e of x is e of x, e to the x, and the integral is e to the x. So it's all the same. The only time it might slightly change is if you have like e to the 3x or e to the 4x, because I'll show you how that would work out. So let's say we have e to the 2x. So we know the exponent rule is to multiply it. So here, we would just multiply the top. So we would get 2x. Oh no, actually this is uv. So ignore this actually. Let's say we're taking the integral of e to the 2x. So we know u in this case, so normally it's e to the x, but instead of x, it's 2x. So u would equal 2x. So du means the 1 above the x comes to 0, and then 2 just stays. So we have 2 dx. And as you can see, there is no like 2 here. I just added that. It's not there. So we need to make it be like a 1 here, basically. So how we do that is we have to make sure 2 here becomes a 1. And we can do that by multiplying du by 1/2. So 1/2 du equals technically 1 times dx, which is just dx. So now we can rewrite it. So we have the integral of 1/2 of, we can keep the e, it's kind of like a cosine or a sine where you just keep it there. E to the u, which is 2x, e to the u, du. So now we know we can take out the 1/2. And we know the integral of e to anything is the same. So we can keep that. And then the u is just substituted. So now we just have 1/2 e to the 2x. And then we have to add in the plus c because it's not a definite integral, and only indefinite integrals need a plus c because you don't know where the stop and like, yeah. So now let's look into definite integrals. So you'll see this a little bit possibly in certain chapters of AP Mechanics. Definite integrals are just integrals with like basically 2 numbers. So it could be like a 4 and a 2 of 5x squared is an example, dx. So basically what you have to do, the first step is just to take a regular integral. So like we did before, the integral of 5x squared dx would just be, we'd have a 3 here and a 5/3 here. So now we change this bar to make it look like this. And we put the 4 here and the 2 here. This means it has already been like taken the integral of. So now we just plug it in. So the 4 is the first number. Whatever's on top is the first number you have to do. So it's basically going to look like this. So instead of the x, we put a 4. And then on the next part, we always have a minus sign in between one term to the next. So this is 1 right here. And then we have the next term, which is just the next variable. So here it was 4, and now it's going to be 2. So basically, you just have to solve this out. So 4 cubed is 4 times 4 is 16, times 4 is 64. So it'll be 64 times 5/3, which is, let me do this real quick. 64 divided by 3. Oh, it's not an even number, so I'm not going to solve it all out, but it's basically 64 times 5/3 minus 2 cubed times 5/3. In this case, you don't need a plus c because it's a definite integral with numbers over here. Now let's look at some applications of what we just talked, because this is mostly AP Calculus, AB or BC, but it's used a lot in physics, especially mechanics. So basically we have different, for kinematics, we have position, which is often terms as x, in terms of time. So position in terms of time. So, and then we have velocity and acceleration. And this is actually the same for rolling motion. It's just a little bit different. So in position, our unit would usually is meters, or it could be centimeters. It could be anything, but the scientific unit for position is meters. So velocity is meters per second. And acceleration is meters per second squared. So let's say you have an equation for position. So it might get, like on the AP test, it might give you like a position equation. So it might tell you the function for position is this. So for example, let me write it out. It might tell you something like x equals 4t squared, and t means time, so it might be in seconds, plus 3t. And it might be asking you to find something such as the velocity. The velocity at time equals 3 seconds. So after 3 seconds, how fast is it moving? That's basically what velocity is. And in this case, you might think, oh, I only have the position function. But actually, you can use position function using calculus to find the velocity. So basically, to go from position to velocity, you just take the derivative. And to go from velocity to acceleration, you just take the derivative. So basically, if you want to go from position to acceleration, you just take the second derivative, which is basically just the derivative twice. So in this case, we have 4t squared plus 3t. And the derivative of that, we learned before, would be, we have to multiply the exponent by the number in front. So 2 times 4 equals 8. 8. And 2 minus 1 is 1. So just 8t. And now we know the number in front here is technically 1. So 1 times 3 is 3. And the t to the 1 power is just subtracted to make it equal to 0. So now we know the velocity function is just v equals 8t plus 3. Now let's say we wanted to find the acceleration function. We have to take the derivative again. So the derivative of 8t plus 3 is just 8. So in this case, if we want to know the velocity at time 3, we have to figure out which is our equation for velocity, which is this one. And so we plug in 8 times 3 plus 3 equals 27 meters per second. Always remember your units. So that's basically how you go from position to velocity to acceleration. So let's say we know the acceleration function. In this case, you would just have to go backwards. So the backwards of derivative is just integrals. So if you have the acceleration function, you just have to take the integral. So acceleration to velocity, take the integral. Sometimes you're given an initial value and you'll have to use that to find the equation. And you can use that with the C value, but we'll cover that in later videos. So now let's find some more examples of derivatives. So you'll see that on the exam, you'll have a formula sheet, and that actually can help you a lot. And it also provides derivatives, but you have to like understand how to use them. So let's take a look at this one. So as you can see, there are actually a lot of derivatives on here, and you might not even realize it. So for example, this one, anytime you see the line I equals the integral of r squared dm, that's basically, you have to take the integral, and you might have to use that to find the center of mass. But let's start with some other easier questions. So as you can see, F equals MA, which I'm pretty sure it's just a basic thing of physics. So let's start with that. F equals a lot of things. So certainly it does equal F equals MA, but it can also equal, since you know that acceleration is the derivative of velocity, it equals m times dv over dt. And basically what dv over dt means is the change. D kind of means change because, like, as you remember, slope is derivative. So d derivative, basically d kind of is slope. And since slope is change in y over change in x, you can kind of use that for any variables that you want. So in this case, our change in y is velocity, and our change in x is time. If you had like a graph, which I will draw, if we have t here and velocity here, let's say we have some function.
Hold on, Mash. I thought how much you're about to give me off of that towards 750. I'm good.
Did you ask a question? I couldn't hear what you said. One moment.
Maybe he accidentally unmuted his mic.
Okay. Okay, we'll just continue. So the derivative of velocity is acceleration. So basically we're gonna want to find where the slope. So let's say right here is t equals 2 seconds. So we can label as a point here. So here we know the velocity, let's say it could be 5 meters per second. But in the F equals ma, we need to find the acceleration, which is the change in velocity over change in time, which is also known as a slope. So here we would just find the literal slope right here. And that's basically how it works. And if you only have the position, you can take the second derivative. So it'd be m equals m times the second derivative of position. So now there's another equation you might have noticed. It's F equals dp over dt. And P equals momentum, which we'll go into later videos, but we'll just give an overview here. So basically, if you're given the momentum, so P equals momentum, you can take the slope of the change, well, not the slope of, but the change in momentum over the change in time, and that will give you the force. And you can also use this to find the momentum if you're given the force by taking the integral. As you can see here, it says J equals the integral of f dt equals triangle P. And there's actually a really useful formula you can use for that. And you have to memorize that. There's actually a frequent question on the AP exam where they want you to take the area, and that will be the integral. So I'll show you how that's done. So J is the change in momentum, which is impulse. J equals the integral, here I'll draw that, of f dt equals change in p. Okay, I just exited that, so I'll have to get that back up. So I'm going to draw it out here. So J is impulse, which is the change in momentum. And the triangle here just means the change in momentum equals the integral of force in terms of time. And this basically would just add in as a dt. So basically what you're gonna have to know here is that if you have a force graph, the integral is the J. So in this case, usually more frequently you have the dp over dt, which is a change in momentum, equals the integral of force. And so as you can see here, it's a simple connection and you won't have to like do much to find it. So if you just have the momentum, you can take the derivative and then to find the integral. So if you can see, if you take the integral here, you just have to make sure it stays in terms of time, because if it's in terms of x, it'll be a lot different. So now let's move on to a different formula. So as you know before, x, you take the derivative of x, it's v, velocity, and the derivative of that is acceleration. So in rolling motion, it's all the equations are the same. It's just everything's a little different. So basically, instead of x, v, and a, you're gonna have alpha. You're gonna have this like w sign, which is basically just it's like the rotational speed. It's not linear speed. So as you can see on here, I think it's on here. It's called angular speed, angular acceleration. And then your x value is not x. In this case, it's alpha. I mean, it's not alpha, it's angle. So theta. So basically, if you have to go from here, you're just going to substitute the values. So to go from theta to angular velocity, you take the derivative. And theta is the measure of the angle. This is angular velocity. So like if you have a wheel, like how fast is it spinning in the angle it is. And then this alpha is angular acceleration. And to go from angular speed to angular acceleration, you just take the derivative again. And angular acceleration is basically how fast is it rotating but accelerating. So that's like pretty simple. It's just like an easy conversion. So here we have another example of calculus. And again, any of these equations you don't need to memorize because you'll be provided them on the physics exam. So let's say we have the work. So we might have to find the work. And the way we can do this actually is often you're given a graph of the force and the time. I'm sorry, not force and time. Force times dr. So in terms of distance, dr. So anytime you have an integral, if you have a graph with this inside, what's inside the integral, you can just find the area. So if you have to take the integral, find the area. If you have to take the derivative, take the slope. So in this case, if we had a force graph, we would just have to take the area of the graph. So like, let's say we have something like this. So let's say we have one rectangle here. So I'm just drawing this, but it's not part of the graph. So we have one rectangle here and a triangle here. So you take the area of the triangle, base times height times 1/2, and the area of the rectangle, base times the height, add the two together, and that's your area. And then your area is literally just the work. So you'd find the area, let's say the area is 16. So that means, and this is F here. So that means here would just be equal to 16, which is your work. Because work is just force times distance. Or it's technically F times displacement. Okay. Let's move on to some other types of derivatives. So if you notice, a lot of times the work is actually just the derivative reorganized. So for example, k equals 1/2 mv squared is actually derived. That wasn't originally like a derivative. What else do we have? So there's a lot of like calculus involved. So for example, we have torque equals r cross theta. And r cross theta is really just rf times f of cosine of theta. So you're gonna have to remember that for the test. So cross. And this is called a cross product. So let me make it up on a bigger screen. So torque equals r times the force times the sine of theta. So basically the angle is just between F and the lever arm. But you have to remember this is sine of theta. So in sine, you're gonna have to take the sine is opposite over hypotenuse. And a lot of times, even though you can do calculus and mechanics, a lot of it can be solved just using simple algebra or trig, like you could see here. It's good to know your trig circle. It's very important. So make sure you remember that, like, basically as you go around the circle, it's like radical 3/2. And then you have to like keep going around and just make sure you memorize everything because that's very important because there's a lot of sine and cosine. And make sure you remember like your rules overall for the different equations, even like not these equations, but other equations that are part of it. So now let's move to center of mass. So this is another basic equation on the test. I equals the integral of r squared dm. So this is actually used for center of mass, where r is the radius. So sometimes you're gonna have to derive the center of mass of objects, and you're gonna have to plug in the r and then take the integral using the dm. And the integral is just the opposite of derivatives. So you'll have to use that to find I, which is center of mass. This is actually a very complicated problem if it like sometimes if there are like multiple parts and the density isn't all linear, which we'll go into another time, but that would take a while. So we're not gonna do that. Okay, let's see what else we have. So another equation where we have to derive work equals f equals negative kx. So in this case, if we want to find the work, we're going to have to take the integral. So as we know before, basically, the integral of force is work. So we're going to have to take the integral of all of this if we want to find the work done. So if k is just a number, like any number, we have to treat it like a number, as if it's like negative 3x. So here we put, since there's technically a 1 here, we have to make it go up. So x to the first power is in reality x squared. And since we have k here, we have to put negative k divided by whatever the number up here is, which in this case is 2. So negative k over 2, x squared. And this equals negative 1/2 kx squared. And this might look very familiar to you. It's the work done by a spring. So this is the force done by a spring. And then this is the work done by a spring, which has different newtons than force. And so this can be used to derive any kind of the work done by a force, which you could see in other forces that aren't necessarily springs. Yeah. So let's see. So now let's move on to this equation, because you're definitely gonna have to use calculus for this, because on the formula sheet it only gives you 1. So x equals x max cosine high t and x max is basically just the maximum it will stretch before it comes back to equilibrium. And equilibrium is basically just when it's like in the middle and it's balanced. And depending on the problem, it might actually not be cosine, but you'll see later in other videos. So x, let's say for now we have x max cosine of wt. And as you remember before, w is really angular speed, because this is all angular. So you're going to want to take the derivative of this to find the velocity. So let's say we have, so in here, we're going to have to take the derivative of this. So wt, the integral, so this is just a number, and the t is a variable. So in this case, you're going to have to get rid of the t and make it a w. So it would be x max times w. And remember the cosine, the derivative of cosine is negative sign. So we're gonna have to add a negative here, put a sign here, and what's inside just stays inside. So we have wt. And now let's say we want to take the acceleration. We're just going to take the derivative again. So we know that we have w in here is going to have to pull out again. So w times w is w squared. And we know that the derivative, we still have the x max, so we can keep that. So let me show you the equations. So this is actually the equation if it's only in simple harmonic motion. So as you can see before, this, we'll go into this later, but I'll give you guys a starter. So this is equilibrium at x equals 0. This is the second one down is when it's stretched all the way. So that would be the x max. And then the compressed is when it's stretched all the way. So x max, but negative. So basically what we're gonna have to use is we're gonna have to use the basic equations. So here is what we can see. So as you can see here, we have x max is equal to amplitude, which is used with a capital A. So instead of x max, you could use A. So here we're gonna use A to represent it. So we could just keep it in terms of here, but I think it's easier if we have using the A, because A always stays the same. It won't change to like V max. Amplitude is always the largest stretching point. So we'd have, let me get this. So it's still X max. It's just we're using A because it's easier to use. So A, and then we have A here, negative AW, sine WT. And then if we go to backwards again to the cosine, so we know the derivative of sine is cosine. So we're gonna have to write cosine there.
Like anything in particular, sugar maybe, but it's at least different than the cinnamon apple. I mean, and then the veggies.
I think you're unmuted.
Forward.
Ryan.
Okay, so we have the derivative of sine is cosine, positive cosine. But the thing is we already had a negative here, so we just bring it down. And now we just keep the inside part, WT. So there's actually a rule I didn't mention before. So when you have let's say we have the derivative of cosine, we did the integral, but if we have the derivative of cosine of 3x, the derivative of that is you keep the inside and then you add the derivative to the outside. So I'll show you how that's done. So just remember these formulas. You just have to take the derivative. You don't have to really memorize it, but it is a lot easier to memorize it. It's just cosine, sine, cosine, A. A stays the same, it becomes negative, negative, and then there's a W squared here. So now let's move on to remember making sure we know all the derivatives. So let's say we have cosine of 3x. And we want to take the derivative. So basically what you have to do is you have to use this, take the derivative of the inside and multiply it by the derivative of the outside. So in this case, we know the derivative of cosine is negative sine. And whatever inside the parentheses, you keep the same. So in this case, it's 3x. The only difference now is you have to take the derivative of 3x. So times the derivative of 3x. And we know the derivative of 3x is just 3 as we went over before. So now instead of derivative of 3x, we just have 3. So our final answer is negative 3 sine of 3x. And there's no plus c when you take derivative, only when you do integral. So now let's move on to one more calculus topic. So let's say we have the ln of 3x, or let's do 4x, we just did 3x. So, and you want to find the the derivative. So basically what this means, there's one rule for when you have ln. It's basically that on the top is the derivative of the inside. So I'm gonna do that. So derivative of inside parentheses. So on top, you have the derivative of the inside of the parentheses. And on the bottom, you have just what's inside the parentheses. So in this case, it would be the derivative of inside the parentheses. So what's the derivative of 3x? It's 3. So we have 3. And what's inside the parentheses is 3x. So we just have 3 over 3x. And this can just cancel to 1 over x. And that's the derivative. So yeah, the basic rule is ln of x equals 1 over x. And you just should memorize this because it's very useful. And so let's say we're taking the integral. So if you see 1 over x, you should immediately recognize it as ln of x. So integral of 1 over x equals ln of x. And in this case, technically, it's ln of x plus c, unless it was a definite integral. So definite integral, no plus c. Indefinite integral, you need a plus c. And so basically, if you have, there are other versions of using definite integrals. So for example, if it's giving you an